Okay, welcome back. In the previous video, we have been talking about the hash tables. We cover both the basic information about hash tables. They have three components: the bucket, the hash function, and with pointers. And we also provide you with an example of a hash table, right? And we also show you how to do the search based on hash tables. So we know how the hash table can provide us with very convenient access to the search in the index table for the data we have in the database systems. However, to maintain this hash table, to have its properties, we have to organize the data we have in the hash table in a better way. So during the running time of our system, we may have to do the insertion deletion of entries in the index table, right? If we plan to use the hash table to help us maintain the index table, and when we do the insertion or deletion, we have to maintain these hash tables in an organized way. It will be very important. And let's assume we still have the example of the hash table as shown here. And right now we plan to do the insertion. We want to insert a pair with the search key equals to D as well as the pointer pointing to the data tuples with the search key equals to D. How can we do the insertion into this table? Let's assume we have the hash function HD equals to 2. We know in the bucket 2 right now we have one blank entry. How can we do the insertion? Right now we have one blank entry in the bucket number 2, right? So we know the HD, according to the hash function, we know HD equals to 2. Then the process to insert it like this. According to the hash function, we find the corresponding bucket for storing the entry. We go to bucket number 2, right? We know right now in the bucket we have one blank entry. If there is space, then we can directly put this D, the search key equal to D, inside the entry. We also have this pointer pointing to the corresponding data tuples in our database systems. So if there is space in the hash tables for storing a new pair, then the insertion process is very easy, also very convenient. We just found the corresponding buckets and put the pairs inside it. Right? You can follow me, right? According to the hash function, we find a corresponding bucket. We traverse among all the entries in the bucket. We know each bucket can store 2 entries, right? The first entry is occupied already. We just go to the second entry. We know this one should be blank, and we just insert this D into it. Also insert a pointer pointing to some data tuples in the entry as well. So this is the insertion if there is space exists. However, in some cases, if all the entries in a bucket have been occupied, and we plan to further insert some new pairs into this bucket, how can we do this? So for some hash tables, they allow us to create some overflow blocks or overflow buckets if there is no space. What does this mean? Let's assume based on the hash table we showed before, the left-hand side, we plan to further insert one pair with the search key equals to K together with one pointer. Right now, if there is no space in the corresponding bucket, we know according to the hash function HK equals to 1. Therefore, we should store this K as a pointer into the bucket number 1, right? However, after we check this bucket, we find this bucket is occupied already. It's full. All the entries have been used. In other words, we can no longer further insert this K into it. Then we can create one overflow block. After this bucket, we have one pointer. We create one pointer pointing to a follow-up bucket. In this bucket, we can also store 2 pairs or 2 entries, right? So therefore, we can further insert this new K into the newly created bucket, and we'll have one pointer pointing to the corresponding data tuples in our database systems. This is called overflow block. It's a follow-up block after this bucket, the number 1, right? So it can provide us with some flexibility for storing more keys into the bucket if it exceeds the bucket size right now, and we can further insert some new pairs into them. If we have a very large index table or hash table, then we may have to create not so overflow blocks, right? Right now, we can only store at most 8 of these key and pointer pairs in this hash table. If we have so many pairs to be stored inside the hash table, we have to create so many overflow blocks after them, right? So this may create some problems actually. So hash table performance is very good, right? Because we have the example for the searching process, and we also provide you with the example for the insertion. The searching and insertion can be very simple if there is no overflow blocks, which you can just go to the corresponding bucket according to the hash function, and we go over the entry inside the bucket to access the pointers pointing to the data, right? So in other words, the hash table can have very excellent performance if there is no overflow blocks. However, the performance can be degraded considerably when the number of keys exceeds the number of buckets. In other words, we can have so many overflow blocks. So you can see the problem, right? If we have so many overflow blocks, before we mention the hash table can be very fast, the main reason is because via the hash function, we can go directly to the corresponding bucket to search for some entries, right? Via the hash function, we don't need to traverse among all the buckets for search for some entries. We can go directly to some buckets, right? However, if we have so many overflow blocks, it will reduce its hash tables for each bucket to a linear list, right? If we have lots of follow-up buckets after this bucket number 1, if we plan to search for some entries with a hash value equals to 1, in other words, we can go to this bucket. However, if this bucket has so many overflow blocks, and we plan to search for some of the keys, then the search process will be just the linear search, right? If we have so many follow-up overflow blocks after it, we have to traverse among all the buckets in the bucket number 1, among all the follow-up buckets, search for some entries. It will reduce its performance of the hash table to the linear list. In other words, it will degrade the performance greatly if we have many overflow blocks. It will just destroy the hash table's performance, right? And besides degraded performance about these hash tables with overflow blocks, we may also have some other problems, either about the memory requirements or dynamic maintenance of the hash table, as well as equality query solely. They may all create some problems for the hash table we have right now.